let's talk about a couple things. First of all, an explicit formula is one where each term in a sequence can be found directly. Okay, so each term can be found directly, and it's from an actual equation, that is. Okay, so only one equation is needed. That's very, very important. So one equation is needed. Okay, and I'm going to go ahead and tell you that that form is going to exist something close to the exponential models that we're kind of working with right now. Y is equal to a times b to the power of x. That's the kind of form it is. Okay, and just so that you know, it will go to something that looks something like this. And we're going to discuss what these parts mean here in just a bit. Okay, so it'll start from a certain number, and then it will basically change as you go throughout, as far as, let's call this a sub naught, and it will be the common ratio, which is what is the change per jump, and it's going to go to the power of x. So let me not get ahead of myself. Let's basically say it's going to look something like the following: a, b, and it goes to the power of n minus 1. And we'll talk about that here in just a bit. Okay, so let's look at what recursive formula means. That was explicit. Now let's look at recursive. Okay, so with recursive formula, we're going to say each term in a sequence is found using the previous one. So each term, it's like one at a time, one by one, if you will, is found, and this is very important, from or using the previous. So the previous term or terms are going to tell us what the next one is. So each term is found from the previous term. Okay, and this one requires more than one. Okay, so more than one equation is needed. More than one equation is needed. And you're going to see here very soon, it looks something like the form of, they give you two equations. They give you where you start, whatever the value is. It could be like, let's say we start at 5. And then the equation after that, which we're going to see, is the recursive formula, which would look something like the following. Okay, so it's like, it could be like 5 times a sub n minus 1. Okay, and we're going to get to that here in just a bit as well. But this is recursive formula versus explicit formula. Okay, so let's keep going. We're developing to this understanding. Okay, so let's look at our first example. It says the table shows the number of subscribers. Okay, so let me go ahead and highlight that. The number of subscribers right here is going to be down here, and it almost looks like this is interpreted as like an X and a Y chart that you're used to seeing kind of vertical with an input and output. But now we're moving on to exponential and logarithmic functions in this unit, to where we're going to deem this as n, and this is a sub n. Okay, yes, you can view this almost like an input, if you will. And then this one would be like an output. But we're going to move it to a deeper understanding with exponential functions, where this input is like the term number. And then this output is going to be, what is that value? Okay, what is the actual term's value? Okay, so we'll say the term's value. Okay, so for instance, let's go ahead and first of all look at what patterns exist, because it's all about patterns. That's what we started the notes off by saying. We want to see what patterns exist. Okay, and there are two types of patterns that you will see here in the next year or two of math. Okay, two predominant ones. You have an arithmetic pattern where you're adding each jump. Okay, and you have a geometric pattern where you're multiplying each jump. In order to solve for an arithmetic, you subtract. So to solve for it and see what pattern it is, you're going to subtract. But to solve for a geometric, you're going to divide. And I'm going to show you that here in just a bit. So first of all, let's go ahead and go to any number here. Let's say that we start near the end of this sequence, okay? The sequence that we have here is basically just a list of numbers. So the sequence is a list of numbers that are showing a pattern. So we could say in a pattern per se. Some kind of pattern. And similar to that one that we first started off on this first slide of trying to find out what is the pattern that exists. Okay, so I'm going to go ahead and save time by showing you that this is a geometric sequence. And it's a geometric sequence because I can take 189 and I can divide it by 63. I can take then 63 and divide it by its previous term, which is 21. And then I can take 21 and divide it by its previous term and get 7. And nonetheless, you get 3 here, you get 3 here, and you also get 3 here. Now remember what I mentioned. You want to at least, to establish a pattern, you need 3 examples. So we have our 3 examples. We have 1, 2, and 3. And if these are all the same number, then we've established the pattern. Because we solved that pattern by division, we know that it's going to be a multiplication geometric pattern. That means to get from 7 to 21, you multiplied by 3. To get from 21 to 63, you multiplied by 3, and so on and so forth. You're going to multiply by 3 each jump in order to get the next term, okay? So that's what patterns are talking about. All right, so now let's talk about something as far as notation goes, because it can get a little bit confusing right off the bat, but we need to understand what these notations mean. Okay, so let's go ahead and start off by saying the now or the present is going to exist as a sub n. Okay, one step into the future, so we're going to say one jump or one step, or what you're going to be used to saying is one term into the future, it's going to be listed as a sub n plus 1. And last but not least, one step in the past. So one step, otherwise one term in the past, like past, present, and future tense, you're going to have a sub n minus 1. Okay, so that's very important because this n is basically saying this one's the first one in line, this one's the second one in line, this one's the third one in line, this one's the fourth one in line. They don't have to be, and this one's the fifth one in line. They don't have to be necessarily 1, 2, 3, 4, 5. We're just going to say that this one is 1, 2, 3, 4, 5. Again, these numbers can be different. You could have started at 10, 11, 12, 13, 14, 15, or whatever. You're establishing the first in line is n is equal to 1. And its value would be 7. Okay, so how do we write that? Well, we're going to say the first term is equal to 7. The second term, or the second person in line, if you will, the second number in line, its value is 21. The third term in line, its value is 63, and so on and so forth. That's how you interpret this subscript, this sub n, okay? So that n is a subscript, if you will. Okay, so now let's rewrite this as far as establishing what is the pattern that we see. Okay, so we're going to say a sub 1 is equal to something, a sub 2 is equal to something, and it's just going to keep going. A sub 3, a sub 4. Again, all we need to do is 3 examples. Let me just do one more for good measure, and then we'll just keep going on and on and on. Okay, so again, it all revolves around kind of this interpretation of the now, the past, and one step into the future. Okay, so here we go. We know that the pattern that we showed, it was multiplying by 3. This goes very, very closely related to our a to the bx kind of exponential model that we've studied in the past couple of days. Okay, this jump or this change by 3 each jump is called our common ratio. Okay, and our common ratio means how much does it multiply in this case, because it was geometric, each jump. Okay, so it would be 3. So 3 is our base. Okay, and then we would have it written to some kind of power. Okay, so let's just put that as x for right now. And then we would have a as far as where's our starting value. Remember, this was our initial value from days past of how we interpret exponential functions. So this is our starting value. So we'll say starting value. Okay, well, our first term that they gave us in our table, the starting value is 7. Okay, so it's right here. So that's going to go right here. Okay, so we're saying that a sub 1, in other words, the first term in line, its value will equal whatever all of this is equal to. But this x right here doesn't really quite match up with this 1 right here. So with recursive and explicit formulas, in this case it's the explicit, we're going to change that to n minus 1. Okay, and we're going to change this to a sub n. So this becomes, if you will, our explicit formula that will work with all of these values that we're searching for. Okay, it'll work with the a sub 2. Let me go ahead and grab all this. Let me do it this way. A sub 2. It'll work with a sub 3. And it'll work with a sub 4. And basically everything in this sequence per se. It's just going to keep going. Okay, and of course it starts with a sub 1. So a sub 1 is our first term. Okay, so now in order to get these values of what they equal, to make sure that we validate and verify our sequence that we're saying it exists as, we're going to go ahead and use this explicit formula here that we came up with. And remember, this is that one formula that we need. We know that it starts at 7. We know that each jump is going to multiply by 3. And all we need to now figure out is how did we label these as far as the first one was 1 for n. In other words, the first one in line. The second one was n is 2. And then n is 3, so on and so forth. And then n is 4, and so on and so forth. It'll just keep going on and on. Now again, just a reminder, these numbers that they gave us in the table that I'm highlighting in gray right now, these numbers just coincidentally were 1, 2, 3, 4, and 5, but they don't have to be. What do have to be the same when you're doing explicit is this n that you're establishing and this n, those are going to be the same per se that you see as far as you're saying the first one in line will equal something. It'll equal all of this. The second one in line, which is a sub 2, will equal all of this, and so on and so forth. These two have to match, okay? And will equal, and then it just goes on and on and on. So let's see what that would be. 7 is our common, or our starting initial value. 3 is our common ratio. And then we have n minus 1. To where if we put in this form, if we put this 1 here for n, then it would be 1 minus 1 is 0. 3 to the 0 is equal to 1. And then 1 times 7 would equal 7. Okay? Notice how I did that with the highlight. So a sub 1 is 7. It's saying the first term's value is 7, which checks out over here on the table. If I did it again, it starts at 7. It changes by 3 each jump. N minus 1 is our go-to as far as with these explicit formulas. This 2, it's like we're going to do it almost like an f of x input, where it would be 2 minus 1, which is 1, 3 to the power of 1, which is 3, times 7, PEMDAS-wise, would give me 21. So that the second term's value is 21, which again matches up right here in our chart that we were given. The first one was 7, the second one is 21. And yes, we just keep going. Okay, so we start with 7, changing by 3 each jump. There's our x. We start with 7, changing 3 each jump, which is our common ratio. There's our x input. So we plug in 3 here. So 3 minus 1 is 2. 3 squared is 9. Times 7 would be 63. So the third term in line's value is 63. Again, verified from the graph. And then a sub 4 would equal from the graph 189. All you need is 3 to establish the pattern, and I used these first 3, and then you have your recursive formula. So the explicit formula, it is one equation is only needed, okay? And that equation is going to be right here, okay? So this is your explicit formula. That means if I wanted to know the 100th term, well, then just plug in 100 right here where n is at. If I want to know the 1,000th term, plug in 1,000 and see what this will spit out. That's your 1,000th term. That's how you're looking at these subscripts of n in the interpretation of the explicit formula. Okay? All right, so now what we're going to do is let's go ahead and look at our next piece. Oops, let me slide down. Our recursive formula. Our recursive formula is a little bit trickier. It's not as easy to interpret per se as far as the explicit formula is. But what we're going to do is we're going to write the equation for the starting number. This needs 2 equations, not just one, it needs 2. The first one is we're going to write the equation for the starting number, or you could say for the first term. Okay, so I'm going to start at this first term, and I'm going to say that that is a sub 1 is equal to 7. That's our first equation, if you will. Our second equation is going to be, what is the pattern? Okay, so what is the pattern that you found? So pattern found from the previous term. Okay, so we found that we were multiplying our previous term by 3. So if I multiply my previous term by 3, what that looks like is okay, let's go back a little bit. Our now term is a sub n. Our previous term is a sub n minus 1. And our term in the future, one jump in the future, is a sub n plus 1. Again, the now, the previous, and then the future term. It all revolves around this, especially when you're looking at recursive formulas. Okay, so recursive formulas are showing you that pattern. Okay, so I'm multiplying each previous term by 3. So let's see what a previous term is going to look like. Well, it's going to be a sub n minus 1. This means a previous term. So if I were to highlight this, that's the previous term. And if I multiply by 3, I'm simply going to say 3 times that. And what that will give me is it will give me the new term. It'll give me the now term, okay? And that's going to be the nth term. And that's a sub n, where this is the nth term. And the reason why I say the now term is because a sub n is the first letter of now. It's an easy way to remember it. The nth term is the now term, the one that you're working with, the one that you're talking about, okay? And then one step into the future makes sense because it's plus 1. And then one step in the past makes sense because it's minus 1, okay? So again, the previous term is going to be one step in the past. So both of these equations, let me go ahead and box these. Both of these equations here and here are necessary in order to create this recursive formula, okay? And a way that you can see it is, what if we wanted to find the second term with this recursive formula? Well, if n is 2, then I would come over here and put this as a sub 2, aka the second term, is equal to 3 times, let's go ahead and put 2 here for n, it'd be 2 minus 1 is 1, it'd be a sub 1. So it's saying 3 times a sub 1, which is 7. Oops, it's 7 up here. Here's a sub 1. That's 7. Well, 3 times 7 is going to be 21. And what is 21? It's the value of the second term, which is exactly what we had over here as far as in our table. That's how the recursive formula works. A sub, right here, a sub 2 is equal to 21 here, and also in the table right there. That's how you're using the recursive versus the explicit. If you need to rewind or pause, please do so just to make sure that you got the difference between the two, okay? All right, let's go to move on to more examples. Let's look at this one. So I could check this by subtracting, and if I subtracting, like I mentioned before, it could possibly be arithmetic, but I can already tell like there's big numbers that are jumps between 36 and 9 and 144 and 36. So it's not going to be subtracting, okay? It's not going to be a subtracting, otherwise an arithmetic sequence. So let me go ahead and subtracting, no. But it could possibly be a dividing pattern, which would show, ooh, I'm going to be multiplying each jump. Okay, so if I jumped here, I'd multiply by 4. Jumped here, I'd multiply by 4. Jumped here, I'd multiply by 4. But again, to find the pattern, it's always kind of best to pick a number and then go to the previous number. Okay, so when finding, I would choose something like 576, and I would either subtract 144 or divide by 144. Okay, then I would take that 144 and I would divide by its previous term, which is 36, and then I would take 36 and divide by 9. And you see that all of these differences or all of these quotients when I'm dividing are going to all, whoops, not equal 9, they're going to all equal 4, 4, and 4. So when finding, we're going to divide something by its previous number in order to see whenever I get my pattern of 3, I am good to go, and that is my pattern. So pattern is multiplied by 4 to get to the next jump, multiplied by 4 to get to the next jump, so on and so forth. Okay, so let's go ahead and go to the explicit. Okay, we know that our first term, we'll say a sub 1, its value is 9. The second term, its value is 36. The third term, its value is 144. And then it just keeps going on and on and on and on. Okay, again, you only need 3. Okay, so with that in mind, I'm saying that from all of this, it looks like it started at 9. Okay, so it started at 9. Its starting value in explicit formula is when n is 1, and it started at 9. So starts at 9. So therefore, all of these equations are going to start at 9, 9, and so on and so forth. A sub 3, a sub 2. And how much is it changing by? Well, it's multiplying by 4 each jump. That means its common base is going to be 4 because it's quadrupling, you could say, each jump. Okay? And then it is like an exponential function where it's raised to the power of x, but because we're working with explicit and recursive formulas, that x immediately becomes n minus 1, n minus 1, n minus 1, okay? Which in this case is saying, if n is 1, then this power would be 0. If n was 2, this power would be 1. If n was 3, this power would be 2. So I'm going to go ahead and write these back out as saying n to the power of 0, n to the power of 1, and n to the power of 2. And it just keeps going on and on. We know that this is 1 because anything raised to the power of 0 except 0 and infinity. So again, anything except 0 infinity raised to the power of 0 is going to equal 1. So that we get 9 times 1. Okay, so a sub 1, whoops, let me write that a little bit cleaner. A sub 1 is 9, which we've already verified. Okay, and then this one would be a sub 2 would go back to that 36. And you see the pattern is in fact going to be when the base is 4. So we go immediately to our explicit formula and we can write it out as the now number or the now term will equal starting from 9 with a changing by multiplication each jump by 4 to the power of n minus 1. Okay, it's saying take the previous number, okay, and basically multiply it by 4. And that'll give you the now number, with the caveat of you are starting at 9. That's what this equation is. So PEMDAS wise, yes, you're going to plug it in for here, n, find out what your power is, have 4 raised to that power, and then last but not least, you would multiply that by 9. And that's what's going on. Here's your explicit 1 equation that you get from the pattern. All right. But the recursive formula, we need 2 equations. We need the first term, which is 9, and then we need the nth term. Okay, so this would be any case scenario. Well, we have to say, again, our equation is the now is equal to the original term. Our first and original term is going to be multiplied with the previous term. Okay, so for instance, let's go ahead and put this as this now is going to be, for this particular one, it will start at 4 and it will multiply with the previous term, which is a sub n minus 1. Okay, let me clean that up a little bit. That looks a little confusing. 4 times a sub n minus 1. Okay, this again is the now term, otherwise known as the nth term. And this is the n minus 1 term, otherwise one term before, or the previous term. Okay, so again, if I wanted to verify with the recursive, it is a little bit different with the recursive. Let's say we wanted to verify this one right here. A sub 3 is 144. Well, if I'm looking for a sub 3 on my recursive formula, it's basically saying n is 3. So n would go here and n would go here. So the third term will equal 4 times the previous term. Okay, so the previous term. And the previous term would be a sub n minus 1. And n, all the while, that I established here was 3. Which makes sense because 3 minus 1 is 2. So here we go. It's saying that the third term will come from the previous term of a sub 2 multiplied with our jump of 4. That pattern multiplication that we found up here of multiplying by 4. That's how the recursive formula works. Okay, you do need 2 equations. You need this initial value and this one in order to establish that in that way. Okay, so again, if I wanted to find, let's say, the first term, let me go ahead and use this again. I'm going to use this exact one here. If I wanted to find the first term, which we already know is 9, okay, we already know that here, then we're saying, what is the first term when n is 1? Okay, so if n is 1, we'd say a sub n, that's where that 1 goes. Then we put another 1 where this n is at, so these two n's. So it'd be 1 minus 1, which is 4 times a naught, which is a sub 1. Okay, and a naught in this case is going to be our initial value per se. Okay, so our initial value, you see here, our initial value is 9. So 4 times what? We don't know what this is per se. And we can't say that a naught is 9 because our initial value was given to us as a sub 1. Okay, so a sub 1 is 9. That's how we're going to get the ones going forward. Okay, so you're not going to be able to necessarily do it this way to make that happen because you're starting from here. Okay, so you can only use these 2 equations to verify everything from a sub 2, a sub 3 forward, because you have to use this given initial value in order to make the other ones work. Okay, so again, the first term, in order to get 9, we're going to say would be 4 times this, and this basically is going to be, everything is 9. It just like, it almost like replaces it and says that everything is 9. Okay, and then again, we just go from there. The second term will be 4 times the first term. The third term will be 4 times the second term. The fourth term will be 4 times the third term. And it's because we're putting into this recursive formula n is 2, n is 3, n is 4, and so on and so forth. So again, if you need to pause, rewind, or whatever you need to in order to get that, please do so. All right, our last example, or last couple of examples that we have here. We have the function is explicitly given, and it's y is equal to a times 2 is the common ratio. It basically doubles each jump, and it's raised to the power of x. So we're saying if x equaled 0, well, 2 to the 0 is 1, times 8 would give you 8. So then y would equal 8. This right here is your starting value. Okay? N isn't 0, but x is 0. Okay? So when you start, and this is where that 0 comes into play that we've kind of been talking about, that I was saying earlier, that last slide where it was a sub 0, and I was trying to show you that if this is 0, that is your starting value. It's actually if x is 0, that's your starting value. But then when you transition over to those n's and those n minus 1s or n plus 1s, that's whenever you're basically saying that this n is your first one in line. Your starting value is when n is 1. Okay? So a sub 1 would equal 8. And the reason why that worked is because x in this explicit model is 0. Okay? So then if I were to keep going, I would have from this explicit model right here, I would have a sub 2, a sub 2 is going to take this 8 that we have, and we're going to multiply by 8, because that's how much we're, actually, let me change that. We're going to multiply that by 2, because each jump is a times 2. Each jump is a times 2. Remember, this common ratio, or this base, is that pattern that we were talking about over here as far as being 4. That's that base, okay? So we would take a sub 2 is going to multiply by 2 to get 16. A sub 3 is going to multiply by 2 to get 32. And then it just keeps going on and on and on. 64, and it keeps going. And the reason why is because this is our starting value. We are going to double each time, and then we raise to that power as far as what we're looking at. In this case, we're saying that we're going to, a sub 2 is going to be 8 times 2. Okay, that's what this one was, 8 times 2. And then this next one was this 16, otherwise this 8 times 2 squared. And then this 8 times 2 cubed, and so on and so forth. Okay, because again, you're multiplying by 2 each jump as you go down. Okay, and then let's see. I believe that's it. So we'll just write it out as far as write out a recursive model. Well, we know our first term is 8, which is right here. And then we know our now term will come from our previous term. And then because of this change of base right here, multiplied by 2 each time. So our recursive comes from this. So remember, the recursive formula has to have 2 equations, where the explicit formula, which is right here highlighted or boxed in black, is just 1 equation. They mean the same thing. Okay, so I just want to make sure that you understand real quick before I'm almost finished with this video. The recursive formula is saying here that the first term equals 8. And we would put that as far as up here as saying x is equal to 0. So the first term down here is when n is 1. Okay, this is a huge difference. This is what you should have gotten from all of this. When n is 1, that's our first term in the recursive formula. But when x is 0, not n, but x is 0 in the explicit formula, okay, then that's whenever you would get your initial value. Your first term comes from when x is 0, okay? That's the difference between explicit versus recursive.